Have you ever wondered what would happen if time stopped? Before Einstein, time was thought to be an immutable constant, always running at the same pace. However, the theory of relativity revolutionized our understanding, showing that time can vary depending on speed and gravity. This opens up the possibility that time could one day stop completely, resulting in the end of all events and new beginnings. Imagine a universe where everything freezes in an eternal moment, with no past, present, or future. This concept is profoundly disturbing for scientists and philosophers. They incessantly debate the nature of time and whether it can truly have an end. Some theorists suggest that under extreme conditions, such as in singularities or the Big Crunch, time could cease to exist. But what would this mean for the universe and for us? If time stops, all changes would cease, entropy would reach a maximum state, and the universe would enter a kind of thermal death. It is an idea that challenges our understanding and ignites our curiosity. Scientists continue to explore these possibilities through complex theories and experiments. The search for answers leads us to question our own existence and the fabric of the universe. Are we destined for an end where time dissolves, or will there be a new form of continuity? This mystery drives us to explore singularities, where the laws of physics, as we know them, break down, and new realities may emerge. Singularities are regions of space where the laws of physics, as we know them, fall apart. The most well-known example is the Big Bang, the point of infinite density from which the universe supposedly emerged. Another fascinating singularity is black holes. Within them, time can effectively stop while continuing to flow outside their boundaries. Imagine being inside a black hole. To an external observer, time appears to drag until it completely stops, creating a paradox that challenges our understanding of reality. Black holes are a true mystery to scientists. They are regions of space where gravity is so strong that not even light can escape. At the heart of a black hole, we find the singularity, where density is infinite and time may come to an end. These extreme regions challenge all our theories and show the limits of our understanding. Scientists believe that studying these singularities can reveal new laws of physics and help us better understand the universe. Singularities are not just a theoretical curiosity, they have real implications for our understanding of time and space. If time can stop within a black hole, it suggests that time is not a universal constant but a variable that can be shaped by the extreme conditions of the universe. This idea leads us directly to Einstein's general theory of relativity, which suggests that gravity affects time, slowing it down near massive objects. Einstein's general theory of relativity revolutionized our understanding of time and space. It suggests that gravity is not just a force but a curvature in spacetime caused by massive objects. This concept helps us understand why time slows down near large masses, such as planets or stars. Imagine being close to a black hole. Time would pass more slowly for you compared to someone far from this intense gravitational field. This distortion of time is one of the most fascinating and disturbing aspects of modern science. General relativity leads to scenarios like the Big Crunch, a hypothesis about the ultimate fate of the universe. If the universe stops expanding and begins to collapse, all galaxies, stars, and planets would come closer and closer together, increasing gravity to extreme levels. Eventually, time could stop completely as the universe collapses into a point of infinite density. This scenario challenges our understanding and evokes a deep sense of mystery about the future of the cosmos. This concept that gravity can affect time not only challenges our daily perceptions but also opens doors to new theories and discoveries. It shows us that the universe is much more complex and dynamic than we ever imagined. By exploring these ideas, we begin to understand that time and space are interconnected in ways we are still unraveling. This understanding leads us to consider the profound philosophical implications of these discoveries, something philosophers have debated for centuries. The nature of time has always been a central theme in philosophical debates. Immanuel Kant, for example, argued that time is a fundamental structure of the human mind, necessary to organize our experiences. He believed that time did not exist by itself in the universe but was a form of perception imposed by our senses. In contrast, Aristotle saw time as a measure of change and movement, something that existed independently of our perception. These conflicting viewpoints show the depth and complexity of questions about the nature of time. An intriguing debate is that of Richard Swinburne, who argues that it is logically impossible for time to end. For Swinburne, time is a continuous flow that cannot be interrupted. He suggests that even in extreme scenarios like singularities or the Big Crunch, the concept of the end of time is incoherent. This raises fascinating questions about the infinity of time and whether it can truly be understood or explained. This philosophical debate challenges us to think beyond the boundaries of science and consider the fundamental nature of reality. These philosophical discussions not only fuel intellectual curiosity but also influence modern science. Many scientists draw inspiration from these debates to develop new theories and hypotheses. The quest to understand time leads us to explore the frontiers of theoretical physics, where scientists attempt to unify general relativity and quantum mechanics. This search for the quantum theory of gravity promises to open new doors and reveal more about the mysteries of time. The quantum theory of gravity is an ambitious attempt to unify Einstein's general relativity with quantum mechanics. While general relativity explains gravity on large cosmic scales, quantum mechanics describes the fundamental forces that govern the behavior of subatomic particles. However, these two theories, fundamental to modern science, are incompatible in certain contexts, such as within the singularities of black holes. Scientists are developing a theory that can combine these two worlds and perhaps solve the mystery of singularities. Advances in quantum gravity theory could provide us with a deeper understanding of how time and space interact under extreme conditions. For example, a unified theory could explain what really happened in the first moments after the Big Bang, a time of infinite density and temperature. This theory could also reveal how time can behave on quantum scales, where classical physics laws cease to apply. This field of study is highly speculative but also an exciting frontier of modern science. In seeking a theory that combines relativity and quantum mechanics, scientists hope to answer fundamental questions about the nature of the universe. They seek to understand whether time is a fundamental entity or an emerging property of quantum interactions. The answer to these questions could completely transform our understanding of reality and open new possibilities for scientific exploration. This quest leads us to face the paradox of the Big Bang, where the universe began from a point of infinite density. The Big Bang is the widely accepted theory about the origin of the universe, suggesting that everything began from a point of infinite density. This point, known as the initial singularity, represents a paradox for scientists because the laws of physics, as we know them, do not apply under these extreme conditions. This suggests that our current understanding is incomplete and that we need a more comprehensive theory to fully explain the beginning of the universe. The Big Bang paradox raises fundamental questions about the nature of time and space. The idea that the universe began from a singularity challenges our understanding of causality and the sequence of events. If time and space emerged from the Big Bang, what existed before? Some physicists theorize that singularities indicate the limits of our current theories, such as general relativity and quantum mechanics. They believe that a unified theory, like quantum gravity, could resolve these paradoxes, providing a deeper understanding of the universe and its origin. This mystery is not just a scientific curiosity but also a window into understanding the fundamental structure of reality. The search for answers leads us to explore ideas like cosmic cycles, proposed by Roger Penrose, which suggest that the universe may go through infinite cycles of Big Bangs and Big Crunches. In this theory, the end of one cycle leads to the beginning of another, creating an eternal continuity of cosmic birth and death. Roger Penrose, a renowned theoretical physicist, proposed a fascinating idea known as cyclic cosmology. According to this theory, the universe did not have just one Big Bang but goes through endless cycles of Big Bangs and Big Crunches. In each cycle, the universe expands, ages, and eventually collapses into a point of infinite density, only to be reborn in a new cosmic explosion. This model suggests that time and space are eternal and recurrent, offering an intriguing solution to the Big Bang paradox. These cosmic cycles imply that our current universe is just one chapter in an infinite story of creation and destruction. Penrose argues that after the total collapse of the universe, all mass particles would disappear, leaving only radiation. In this state, the universe would lose all information about its past, allowing a new Big Bang to occur without the constraints of the previous cycle. This theory challenges the idea of an absolute beginning and leads us to think of time as a series of cyclical events rather than a straight line. The theory of cosmic cycles not only challenges our perceptions of time but also opens new possibilities for theoretical physics. It suggests that the structure of the universe may be more complex and interconnected than we imagine. The idea that time can lose its fundamental characteristics, such as duration and unique direction, in certain extreme states, is both disturbing and fascinating. The duration and direction of time are fundamental concepts that shape our understanding of the universe. Normally, we perceive time as a straight line flowing from past to future. However, in extreme states like the heat death of the universe, these characteristics can disintegrate. Heat death is a theoretical state where the universe reaches total equilibrium, and no useful energy remains to do work. In this scenario, the difference between past, present, and future becomes irrelevant, and time loses its meaning. This concept profoundly challenges our everyday perception. If time loses its characteristics of duration and direction, what would that mean for the universe and our existence? Scientists explore these ideas through advanced theories and simulations, trying to understand how time can behave in such extreme conditions. The idea of a universe without a clear sense of time leads us to question the nature of reality and our experience within it. These reflections lead us to consider how time can merge with space under certain extreme conditions, such as in black hole singularities. In these regions, space-time may behave in ways we do not yet fully understand, revealing new dimensions of reality. The fusion of time and space could offer us a new understanding of the universe, where these two entities become indistinguishable. The concept of space-time, introduced by Einstein, unifies space and time into a single entity. This revolutionary idea suggests that events in the universe are defined by their coordinates in space-time, where gravity can curve this structure, influencing the passage of time. In extreme conditions, such as in black hole singularities, this fusion between space and time becomes even more complex and intriguing. Inside a black hole, time and space behave in ways that challenge our everyday understanding. Research suggests that under certain extreme conditions, time could merge with space, creating new dimensions of reality. This implies that deep within black holes, time can stop or even become irrelevant, while new forms of space emerge. These ideas are fascinating and disturbing, suggesting that our understanding of the universe is just the tip of the iceberg. Scientists are exploring these possibilities through theories like quantum gravity, hoping to uncover the fundamental laws that govern the universe. This fusion of spacetime in extreme conditions opens new perspectives for theoretical physics and cosmology. It invites us to reconsider fundamental concepts and explore new dimensions of reality. As science advances, we continue to unravel the mysteries of the universe, revealing a complex and interconnected tapestry where time and space are just two aspects of a deeper, multifaceted reality. And with that, we conclude our exploration of the time paradoxes that disturb science. Exploring the paradoxes of time leads us to question our most basic understanding of the universe. From the possibility of the end of time to enigmatic singularities, we navigate through theories that challenge the laws of physics and open new doors for scientific investigation. These theories not only fascinate us but also invite us to think beyond the obvious, to consider the nature of time and space in completely new ways. The idea of cosmic cycles and the possibility that time can lose its fundamental characteristics in certain extreme states are both disturbing and inspiring. They remind us that even with all our knowledge, the universe still holds many secrets. If you enjoyed this journey into the unknown and want to continue exploring the mysteries of the cosmos, subscribe to the channel and turn on notifications. Join us for more scientific adventures and continue to expand your mind with the wonders of the universe. Until next time.